Hey everyone, welcome back to another explainer. Today, we're diving into something really fascinating, the I2C bus. Now, usually, we tend to think of digital buses as these highly organized, perfectly peaceful highways of information, right? But it turns out, if you look closely at the physical layer, it's actually a silent, highly deterministic, and utterly ruthless battleground. And understanding exactly how this battleground works, well, that's the key to unlocking true systems-level mastery.
So, let's start with the fundamental mystery we're exploring today. Just imagine you've got a multi-master system. Two microcontrollers, let's call them Master A and Master B, are sitting on the exact same bus. And they both decide to start transmitting data at the exact same microsecond. Now, in almost any other digital protocol, this spells absolute software disaster. You're talking corrupted packets, massive CPU interrupts, forced retransmissions, and just a whole lot of software overhead trying to untangle the mess.
Normally, you'd totally expect a catastrophic bus collision. I mean, in a standard protocol, if one chip pushes high voltage and the other pushes low, you literally get a short circuit. Things heat up, data gets completely destroyed, and the software throws a massive error. But I2C? It doesn't do this at all. Instead, it uses raw hardware physics to silently resolve the conflict. Neither chip fries, the bus doesn't crash, and remarkably, the winning chip's software never even realizes it was just in a fight.
Section 1. Weapon of choice, open drain physics.
To really understand this silent victory, we have to look at the protocol's electrical foundation. It all comes down to a very specific type of hardware design called open drain, or open collector, architecture. Think of a standard push-pull output, like a giant mechanical game of tug-of-war. If one master pushes up to 3.3 volts and the other pulls down to ground, they are fighting each other directly. Boom, short-circuit risk. Open drain is completely different. In open drain, the microcontrollers never actually push voltage onto the line. They only have the ability to pull the line down to ground. If they want to send a high signal, they just let go. They release the line, and a passive pull-up resistor on the bus simply floats the voltage back up to high.
And that brings us to the absolute unbreakable rule of the I2C battleground. A 0 is dominant and a 1 is recessive. Because these tiny internal field effect transistors, or FETs, can only actively pull the bus down to ground, a logic 0 represents a dominant physical force. A logic 1 simply means releasing the bus. So if Master A releases the bus to send a 1, but Master B pulls it to ground to send a 0, the physical copper wire is going to go to ground. The 0 will always crush the 1.
But how do the chips actually know this is happening? Well, that's where the hardware check rules come in. In I2C, every single master must constantly sample the SDA, the serial data line, while it's transmitting. It's this continuous, real-time feedback loop. The master sends a bit out and immediately reads the physical wire to see if the voltage matches what it just tried to send. If a master outputs a 1, expecting the line to float high, but it reads a 0, it instantly knows another master is pulling the line down, and that mismatch means arbitration is instantly lost.
Section 2. The bit-by-bit duel.
Let's actually slow time way down for a second and watch a synchronized microsecond-by-microsecond duel between Master A and Master B. By pure chance, both masters start transmitting simultaneously. Their first few bits match perfectly. A 1, a 0, a 1. Because the waveforms align so perfectly, neither chip even realizes the other is there. But then we get the divergence. Master A wants to send a 1, so it releases the bus, while Master B wants to send a 0, so it pulls the bus to ground. In a fraction of a microsecond, Master A checks the bus, expects a high voltage, but sees ground. It's been crushed. It instantly yields, shutting off its data driver, and seamlessly transitions into a receiver mode. Meanwhile, Master B just keeps right on transmitting its data, completely unbothered.
And honestly, this is exactly why the I2C protocol is such an architectural triumph for embedded system resilience. Because this arbitration is handled purely by the open drain physics and the hardware layer, there is zero software overhead. Master A's hardware handles the retreat entirely on its own. Master B never experiences a collision, which means absolutely no packet retransmissions and zero wasted clock cycles. It is just incredibly elegant.
Section 3. The need for bus buffers. Because, physics gives and physics takes away. We kind of have to pivot from the brilliance of this protocol to the harsh physical realities you face when you actually try to scale this up in a real-world system. Anyone who's designed a complex embedded system absolutely knows this headache. You start adding more slave devices, EPROMs, temperature sensors, LCD drivers, and suddenly things just randomly stop working. Every single device you add and every inch of copper trace you route across your printed circuit board acts like a tiny capacitor, And before you know it, your bus is heavily burdened with capacitance.
Because here are the strict physical limitations we run into. The I2C specification states that the internal FETs of a microcontroller generally only have about a 3 milliamp drive strength. That tiny amount of current has to overcome the capacitance of the entire bus. If you surpass the strict 400 picofarad bus capacitance limit, those crisp, beautiful square digital waves turn into sluggish, distorted curves. The rise and fall times get completely destroyed, and suddenly, that precise bit-by-bit duel we just talked about, it completely falls apart because the chips just can't accurately read the voltage levels anymore.
And this problem has literally only gotten harder over time. Just look at the evolution of I2C speeds. Back in 1992, fast mode was just 400 kilobits per second. By 1998, high-speed mode pushed it to 3.4 megabits. And in 2013, ultra-fast mode hit an incredible 5 megabits per second. As bandwidth demands exploded into the megabits, maintaining clean signal integrity against that 400 picofarad limit became the ultimate engineering challenge. You simply cannot drive a heavily loaded bus at megabit speeds with a tiny 3 milliamp transistor.
Section 4. Architectural Impact and Limits.
So how do we actually solve these physical bottlenecks? We use hardware solutions like I2C bus buffers. These things are basically magic for an electrical engineer. They sit right in the middle of your bus and literally divide the capacitive load in half, isolating the two sides. They also enable voltage level translation, meaning a super modern 0.8-volt CPU can seamlessly duel with an older 5-volt sensor on the exact same network. By actively driving the signals, these buffers greatly extend your maximum trace length and really help punch through environmental system noise.
Now, whether you use a static or incremental offset buffer, they're both designed to safely manipulate these delicate logic levels on the physical wire without breaking our core rules. But there's actually another twist here from multi-master setups dealing with different speeds, and that's clock stretching. Through similar open drain physics on the SCL line, the clock line, the slowest device can literally hold the clock low, acting like a giant physical AND gate to force faster masters to wait. It's just another brilliant way hardware physics silently controls the flow of data.
Which brings us to a pretty profound takeaway for your own system architectures. Think about this. If 0 is always the dominant physical force, devices with lower I2C addresses inherently possess a higher priority on the bus. An address starting with a bunch of zeros is always going to crush an address starting with ones. So how is that raw physics-level reality dictating the hierarchy of your embedded designs? It's definitely something to think about. If you found this journey through the hardware layer fascinating, and you want to see how silicon handles data movement after arbitration is won, without the CPU even being involved, you should totally check out our explainer on direct memory access, or DMA. It perfectly complements what we've covered today. Until next time, keep exploring the physical layers behind your code.